Good afternoon. On behalf of the School of Physics and on behalf of the university, it gives me great pleasure to welcome Professor Srikanth from the University of South Florida, Tampa, Florida, USA. He'll be giving a distinguished lecture on the tuning of magnetic anisotropy in nanostructures for biomedical and electromagnetic applications. As you are probably aware, the distinguished lecture series was begun in 2007, and we have about 6 to 10 distinguished lectures every year. And this is a fairly successful series where we have been able to listen to some very interesting talks. So may I request Professor Arun Agarwal, our Pro Vice Chancellor, to preside over the...
I am here in my role as a past chairman of the IEEE of the Hyderabad section, and in fact Professor Agarwal was my much senior in the IEEE of the Hyderabad section. So we are all very happy to have the speaker here, with whom I share the Alumni Association of the Indian Institute of Science. So that is another common thing which we have. So it gives me then immense pleasure to be here to be speaking about these two things. So the small thing which is there about IEEE is, or rather it is the distinguished lecture program of IEEE, where every society, the speaker here is a distinguished lecturer in the Magnetic Society. So that is the Magnetic Society of IEEE sponsors the travel and other visits of the speaker over not just over the world, that is, and we are really happy that he is touring presently our country. And IEEE in Hyderabad has been very active. They have won at least 3 times. They have won the large section award of the Region 10. So that is a great achievement of the IEEE Hyderabad section. And there are many chapters in the IEEE Hyderabad section. Many of you may find interest in joining those chapters and partaking of the activities. Okay, so the IEEE also is a worldwide organization, and all these activities will be also under that umbrella. Just for a numeric thing, more than 400,000 is the membership of IEEE, and here in our university also many activities are taking place, and we also have a student branch for those students who are interested to join. There is a student branch as well. Okay, so I thank once again this occasion given to me, and we'll move on with the proceedings. Thank you.
I welcome you all, and it is indeed a warm welcome. It's quite hot. And respected members on the dais, Professor Srikanth, our distinguished lecture series speaker from University of South Florida, Professor Rajaram, Professor Srikanth, Atul Negi, and all the faculty members, staff, students, invited guests, ladies and gentlemen. It gives me immense pleasure in welcoming all of you to our university, which has attained a very unique place as a major institute of academic excellence in higher education and research. The University of Hyderabad, a premier institution of postgraduate teaching and research in the country, was established by an Act of Parliament on 2nd October 1974 as a central university, wholly funded by the University Grants Commission. The current academic structure of the university is its 12 schools, 19 departments and 21 centers, and several specialized centers such as CMSD, ACRAHAM, etc. We have over 5,000 students, and 1/3 are into their MPhil and PhD program. Over the years, our faculty members have been honored with several national and international fellowships and awards of leading academia in India and abroad. In our journey of close to 44-45 years, and based on the QS rankings, we are now among the top 600 institutions globally. 106 in Asia, and in India we are 7th after IITs and IAC and probably first among a multidisciplinary universities. Our university also has been placed in the top 100 in the world with its achievement in the first 50 years by the QS World Ranking. This is the highest ranking for a multidisciplinary public and non-affiliating university in India. There is also a BRICS ranking which QS has come out with. Under BRICS we are ranked 36, and we are one of the only 2 universities to be bestowed the honor of Category 1 of the graded autonomy of MHRD UGC. And we are also accredited by NAC with a A grade with a CGPA of 3.72, which is probably the third, is the highest in the third cycle of accreditation. Further, in order to harness our research potential and to promote innovation and entrepreneurship among the faculty and students, our university has established what we call as a technology industrialization and entrepreneurship unit at university. The TIU will be the knowledge repository of the university, innovation, intellectual property right and entrepreneurship on the campus. And TIU will also act as a face of the university for industrial relations and foster industry-academia interaction. We have also launched an Aspire, which is a non-profit Section 8 company, has been incorporated to engage in technology business-related activities, and there are also 3 incubation centers called TBI, Tide and BioNest. All of the above have helped us achieve an eminent position of excellence within the central university system of our country, as indeed on the academic landscape of the nation, as we embark on the journey of a global excellence. Now may I invite Dr. Srikanth to kindly introduce the...
But it doesn't look nice to asking Srikanth to introduce himself. So, yeah. Good afternoon, everyone. I welcome you all to this distinguished lecture. It's a great honor and privilege to introduce Professor Srikanth Herren. He has actually changed his name to Hari Srikanth, so maybe I should go by that. So Hari Srikanth is a professor at the University of South Florida, Tampa. He obtained his BSc and MSc from Madhura College, Madurai, and he received his PhD from Indian Institute of Science in experimental condensed matter area. And later on, after a few years of postdoctoral experience, he has established a functional materials laboratory at University of South Florida, where he is currently the full professor. He has published more than 250 papers and has 2 US patents, and he is a fellow of a number of societies. To name a few, he is a fellow of American Physical Society, Institute of Nanotechnology, a senior member of Institute for Electrical and Electronic Engineers, IEEE, which is actually sponsoring this. He is a IEEE distinguished lecturer for this year. Under this banner, he is actually going around and giving talks. So, and then he is also at Magnetism and Magnetic Materials conference publishing chair for many years, and also in the program committee. That's where I met him for the first time in 2002 when I went to present a paper in Tampa. I never realized that I'll go there again to work later, but that's when I met Srikanth for the first time there. And he is very active in intermag conferences, and he attends conferences internationally and travels extensively, keeps coming and attending conferences. As you can see from the talks today, that he delivers very good talks, and normally people will be encouraged to invite him again and again. And one more important thing, what I've seen him from the last 20 years is that constantly he is getting good funding. So he has generated so far almost of the order of $10 million US from different funding agencies such as National Science Foundation, Department of Energy, Army Research Office, DARPA, Marie Curie Foundation, etc. He has visited many places as short-term and long-term visiting professor positions. And what I heard today morning is that recently he got this Fulbright fellowship, under which again he'll be traveling to Singapore to spend some time there. So he has a quite active group. He has he hires postdoctoral fellows. This is for the PhD students here. So regularly he hires, and I was fortunate to work with him from 2004 to 2006 August as a postdoctoral fellow, and it was very productive. You can simply go and check. With Srikanth and Srinath, probably during the 2 years we have published 20 papers or more. So I really enjoyed the company there, and he was instrumental probably in getting a job back here in Hyderabad University. So I take this opportunity to welcome him here and thank him also formally at this point of time for accepting to give this talk. And I encourage the students to interact with him, because University of South Florida, as you can see, is a very big university where it has a vibrant research as well as education MS programs. So many of you, I wish that you can actually apply there and elsewhere, and then so I wish you to interact with him after the talk personally. Okay, so thank you.
It's a great honor to be here. I would like to thank Professor Agarwal, Professor Negi, and Professor Rajaram for inviting me here, and of course my close associate. And all right, okay, thank you very much again, and it's a great pleasure to be here. I've been to Hyderabad several times, and a couple of times to the university actually, I think. I remember meeting Professor Kerr once and having a wonderful discussion with him on magnetism course. Srinath pointed out that he was a member of my group many years back. It was almost 15 years back. I can tell you that there was another person that I was also associated with as a friend, and someone that we worked together. We did PhD together at the same time. That is Professor Ghanshyam Krishna. We were actually PhD students around the same time at IISc, and that was 25 years back. All right. There's another person that I'm associated with. I mean, you can tell that I enjoy my association with Hyderabad, and that is Dr. Chayita Lahi. She was a former student of USF in my department, and turns out that I was on her PhD committee, and today she accused me that I asked her a lot of difficult questions. In my defense, that kind of brought you here, right? So I'm vindicated. All right. Okay, so it's a pleasure to be here and give this lecture sponsored by the IEEE. I'll say a few words about the IEEE Magnetic Society. Professor Negi has already mentioned about this. This is the largest professional society in the world. Okay, and it has many chapters, and the magnetics chapter is a very active, very vibrant chapter of this society. But before that, let me say that this is going to be a story of how to tune anisotropy in magnetic nanoparticles, specifically for biomedical applications. And in effect, it's for treating cancer therapy. How can we use magnetic nanoparticles for actually killing cancer cells? That's the main intent of this talk. I don't think I'll have time to get to the second part. If you have any other questions about that, we can discuss that later. I'll be here the rest of the afternoon. I would like to thank all these other wonderful agencies that have been funding our work over the years on nanoparticles as well as oxides. Is there an echo that I hear, or is it just me? Okay, you're good, right? Okay. So first, as I said, let me say a few things about the IEEE Magnetic Society, and this is the mission statement, and don't worry, you can go to the website here and read about this. I'll just say a couple of things here. This is a very vibrant society, and of course, you have this distinguished lecture program that allows people, a few people around the world in different areas. They select about 3 or 4 each year and have them go around giving talks all over the world. I'm supposed to give 50 talks this year from January to December. For the members who are already working on magnetism, this is an important society to be a part of. First of all, you have the IEEE tag, IEEE legal. I mean, who can refuse that, right? The other thing is the 2 major professional conferences in magnetism, which is the MMM and the Intermag. You get discounted registration fees for both these conferences only if you're a member of this society. And also for the younger members of the audience, students who are working in magnetism, you have additional incentives. For example, the IEEE Magnetic Society holds a magnetism summer school every year. And this is all over the world in different places, many exotic places. This year, unfortunately, not so exotic a place. It's in Richmond, Virginia, which is a nice town, but close to DC, Washington, DC. But just to give you an example, last year, this conference, the summer school, was in Quito, Ecuador. I would have loved to go there myself. All right, so there are a lot of incentives, so please go ahead and visit this website here, get yourself familiar with this IEEE society, and certainly become a member if you're working in magnetism and related areas. Okay, so I could not take pictures of Hyderabad because I just came here this morning. So this is pictures from Madurai, which is my hometown. My mom lives there, so I come visit at least 3 times a year, come to India. So I'm sure there'll be other opportunities for me to stop by in Hyderabad. I would like to also take this opportunity to invite you to my city where I live. If you want to know about Tampa, there are 2 people right here, Srikanth and Jayita. You can talk to them. They can tell you about the wonderful time that they had here. Let me give you some stats about this university. We are one of the biggest publicly funded universities in the country, in the United States. We are the 12th largest, actually. We have about 47,000 students, 35,000 on the main campus in Tampa, and the rest in branch campuses. And I would like to say a word about the physics department. We offer a PhD in applied physics, and this is the only one of its kind in the state of Florida. There are other major universities in Florida that you might have heard of. University of Florida in Gainesville, which is the flagship university of the state, and also Florida State University in Tallahassee, which is where the National High Magnetic Field Lab is located. But they don't have an applied physics program. So if you want to, and also, by the way, just 2 weeks back, we had the annual ranking come out about the best beaches in the country, and Clearwater Beach is always number 1, and that's actually Tampa Bay. All right. So if you want to be near the best beach in the world, in the United States, and get a PhD in applied physics, we are the only choice. So please pass the word around. Okay, so I'd like to again acknowledge the reason I'm here giving these talks is because of this wonderful group of students. This is the current batch. Of course, Srinath's name would have been there 10, 15 years back. So basically, these are all postdocs that have just recently moved on to find employment in other places. These are the current students here. Some of them have recently graduated. The ones in green are the ones that contributed to the work that I'm talking about today. And we work on a lot of, in the broad area of magnetic materials. We do a lot of work in this area. These are some key words if you're familiar with this. But in principle, this lecture is going to be on magnetic nanostructures as applied to nanomedicine. That's what I'm going to focus on for the rest of the talk. We do a lot of conventional experiments, as any magnetic materials lab does, including Srinath's lab. We do all kinds of magnetization measurements. The other thing that we do in my lab is we have a culture of actually using a magnetometer, like a PPMS or quantum design instrument, as a platform for giving us a range in temperature and magnetic fields. And students sometimes build their own inserts into it and write the coding and everything and integrate it to the system. So we have many user probes that we developed ourselves, user inserts, magnetocaloric effect, mode system, and this is something I'll talk about today, which is actually how to measure the effectiveness of these nanoparticles for cancer therapy. All right, we do what is called hyperthermia experiments. Okay, so the other thing that I want to mention is this is a unique method, radio frequency transfer susceptibility. It's somewhat similar to FMR, and I know that Hyderabad has been very well known in the field of ferromagnetic resonance for many years in magnetic materials. Professor Cowell is a household name in magnetism here. And basically what we do is something very similar, but with this technique, it's done at radio frequency, high frequency. We have very good sensitivity, and we can actually measure the magnetic anisotropy, effective magnetic anisotropy, as well as switching fields, which are the most fundamental parameters that you want to know in magnetic materials. Okay, and this is going to play a key role in today's topic, because I'm going to focus on anisotropic nanoparticles. So the outline is as follows. Magnetic anisotropy is my mantra for today, and as I'm an Indian too, so we all believe in mantras, right? So by the end of today's lecture, I hope this will be your mantra too, because it's as important and as something that can be tuned and something can be used for many applications. Again, that's the main part of today's talk: how to make anisotropic nanoparticles, how to tune the anisotropy, how to measure them, and also how to apply them for various biomedical applications, specifically for cancer therapy. Okay, so let's start with a basic idea of what magnetic anisotropy is all about. First, I would like to say that when you think of a ferromagnet, any kind of magnetic material, this is an outreach talk, so I'm going to keep it very general, so there'll be a lot of introduction for students from many disciplines. So if you take a magnetic material, you can apply an external magnetic field, then the magnetization vector, which is a collection of all these magnetic moments that the material has, let's represent that by this vector m. So this is going to have competing energy scales here. One of them is what we call the Zeeman energy, and that's due to the external applied field that you apply. And the other one is the internal energy, which we call typically anisotropy energy, or magnetocrystalline anisotropy. And it is a trade-off between these two energy scales that determines where this magnetization vector is eventually going to lie. Okay, so as you increase the external field, the Zeeman term will dominate, and then eventually the moments will be in line with the applied field. So we call that saturation. That explains the hysteresis loop that many of you are familiar with in a ferromagnet. And in fact, because this intrinsic energy that the magnet has, which is determined typically by a certain directions where it is easy to magnetize, for example, we call this the easy axis and the hard axis. And depending on how you apply the magnetic field with respect to the internal preferred direction, the shape of the hysteresis loop or the MH curve is different. This is key to today's talk, because we're going to use this possibility of tuning the shape of the hysteresis loop for increasing the figure of merit for this particular application, namely hyperthermia. Okay, so again, this is basically just a simple equation. We just take the uniaxial term because these are mostly nanoparticles. They don't have a preferred direction for the magnetization. But in principle, if you want to look at other directions, you can do that. This is basically a cubic term that you can throw in there if you have a cubic crystal, for example. When it comes to nanoparticles, you have to deal with several other factors here. One of them is, of course, nanoparticles. You have to deal with the surface of particles. And in fact, nanoscience is all about surface science, right? Because most of the properties, physical properties, are governed by surface atoms. So in a sense, surface controls the magnetism too in this case. So surface anisotropy, shape anisotropy is easy to understand. You can actually make particles, nanoparticles, or nanosystems, nanostructures that are rod-shaped, for example. We call them nanorods, nanowires. I'm sure there are a lot of activity all over India in some of these areas. So that induces a specific direction, right? So it's easy to understand, conceptualize that when you apply a magnetic field, it's easy to magnetize this material along the longitudinal axis, for example, of the nanorod. You can also have what is called the striction or strain. When you put two materials together, two magnets together, it turns out that the interface plays a major role in determining which direction or which direction is preferred by the magnetic moments. Configuration is when you bring many particles together, you can form clusters that have distinct symmetries, and that govern, again, the shape of the hysteresis loop. So all of these things can be tuned to tune this particular shape, and that can be used, and that tunes the hysteresis itself, and turns out that it has an immediate or direct effect on the application of these particles for heating and killing cancer cells. Okay, so the next thing is to convince you that anisotropic nanoparticles are not rare. In fact, they are ubiquitous. They're all over. And I'll show you 3 TEM images, transmission electron microscopy images, to give you an idea of how ubiquitous they are. These are 3 TEM images, but the source of these are all the same kind of nanoparticles. They're all iron oxide, magnetite, or ferrite nanoparticles, which are commonly produced in many labs. Turns out that the source where they come from is what makes them interesting. All right. The first one, you can see that these are nanoparticles that seem to be chaining up like that, forming short chains. Turns out that these are found in some bacteria. So there are these magnetotactic bacteria that actually make these nanocrystals of iron oxide, magnetite, which is Fe3O4, and chain them up to make these short chains, precisely what the Chinese did when they discovered lodestone. That was the first magnet. Fe3O4 magnetite is nothing but lodestone, the first magnet that was discovered by the Chinese, that if you make it into a compass, it can be used to, basically use the Earth's field and determine the direction for navigation, right? So that's exactly what these bacteria are doing. They're chaining up these iron oxide nanoparticles, magnetite nanoparticles, and forming little compasses. They use it for trying to navigate towards the source of food, in this case, all right? So the second one is truly out of this world, literally so. Turns out that these are the same magnetite, iron oxide, magnetite nanocrystals that were found in a chunk of meteorite from Mars, okay? And there are groups, it turns out that those of you that are working on nanomagnetism should know this, that many of the key words in nanomagnetism, such as super paramagnetism, for example, which I will explain a little later, and also the physics of nanomagnetism was first studied not by physicists or chemists, but by geologists. Turns out that 1930s is when they started, people looking at magnetism in rocks and various kinds of rocks, and that's how it all started, because most of these rocks have nanostructures, nanoparticles of iron oxide. So that's an example of that. And the third one is man-made. It actually produced ferrite crystals, similar iron oxide nanocrystals, that are produced in a plasma chamber, in microwave plasma, under high energy conditions. All right. So essentially, one thing that you notice is that in all these particles are not symmetric. They're anisotropic. Can you see the faceting of the surfaces and also the elongation when you form chains? So there's an element of anisotropy that's present in all these things. So now the goal is to try to use this to try to see if we can improve the state of the art in some of the current applications where these nanoparticles are used. Okay, so just to give you a summary of that part here, basically you can think of tuning the anisotropy in many ways. One of them is nanorods. In this case, you give a distinct shape anisotropy where you can make these nanostructures, and I'll show you examples of how you make them in a bit. And then here's an example of what we call tuning the surface anisotropy. You can actually make the particles in cube shapes, pyramidal shapes, or these kind of exotic octopods. And all this is done using simple solution chemistry. All right? It's basically controlling the time and temperature of the reaction that you conduct to make these particles. So we can actually make these and play with the shapes. And in principle, we can make any kind of Archimedean solid shapes that one can think of using the right combination of temperature, time, and surfactants that you use for conducting the chemical reactions. Okay, so the next thing is, because by now I told you that anisotropy is very important, so let's try to see if we can find out a way to measure anisotropy very precisely. All right. So just to change time reversal symmetry, I'll move this side here. I think this is a little better for me. Okay, so what we do is we use a technique called radio frequency resonant tunnel oscillator method. That's TDO here, and this method is very sensitive and very precise in measuring anisotropy, vector anisotropy. In this case, the sample sits in an inductive coil, right? And essentially, this forms a tank circuit. This is nothing but an LC tank circuit. Students in the audience have done AC circuits, I'm sure. The only difference is that this is powered by a tunnel diode. And those of you that remember your tunnel diode characteristics, you know that there's a negative resistance region, right? And if you bias it in the negative resistance region, it actually supplies power back to the LC, and that makes it self-resonant. So with this technique, with the tunnel diode oscillator, you can build very precise, sensitive oscillators. Okay? And oscillating typically in the radio frequency range, you can actually change that from 10 to 25 to 30 megahertz or so. Now the sensitivity is that the whole thing is sitting inside a superconducting magnet, which gives a DC field. And like that, for example, that's like a quantum design magnetometer where you put the magnet in. So the DC field is perpendicular to the small modulating RF field. So this is a crossed field. That's why we call it transverse. Okay? And this is very similar to FMR. So that's one of the techniques where we use crossed fields, where there's a modulating field on top of the DC field. It's also very similar to NMR, nuclear magnetic resonance, where you're dealing with nuclear spins, of course, but again, we use the crossed fields, right? So the transverse susceptibility is what we do to look at the anisotropy, and I'll explain to you why we do it this way. But let me say a word about the sensitivity of this technique. All we do is measure the resonance frequency with and without the sample and all that. All right, we put the magnetic sample in there, we measure the shift in the resonance frequency as a function of external DC field that we apply and the temperature. That's all we do. We don't bother even measuring the Q, because Q is lousy. This is just an open coil. Q is 50. We don't even bother to measure that. So just the shift in the resonance frequency can be related to the change in the transverse susceptibility or permeability of the sample. And that's how we get information about anisotropy and switching in ferromagnetic materials. The sensitivity of this technique is that using a cheap frequency counter, you don't need any fancy equipment here. Just a cheap frequency counter, you can detect changes of the order of a few hertz in an overall resonance of 25 megahertz. So you do the math, it's parts per million resolution. So we can actually pick up very fine phase transitions, magnetic phase transitions as a function of temperature and field that you can't pick up even with this squid, with this technique. Okay? So that's the sensitivity of this method. Alright, so why transverse susceptibility? Why go to this trouble of having these crossed fields? And it turns out that we got this idea from an old paper by a famous theorist in magnetism, Amica Maharoni from Israel. He published this paper. This is a calculation of transverse and parallel conventional susceptibility. Remember that susceptibility is nothing but the derivative of the magnetization, right? It's taking the first derivative of your hysteresis loop, MH loop, right? That's what it is. So this is the parallel susceptibility, and that's the transverse, which is the tensor. It's the projection of the magnetization in the perpendicular direction. Okay. So what he did is that he calculated the transverse susceptibility as well as the parallel susceptibility. And this is from a 1957 paper. It's a scan of that, so the quality is not very good. Okay, it was also published in the Bulletin of Israel Physical Society, so it was a bit of a trouble getting it. But that's the actual curve that he plotted. What he did was he did a simple t equal to 0 calculation for a single domain nanoparticle. Okay, Stoner-Wolfram particle. And if you look at this, this is a reduced field here with respect to the anisotropy field. And you go from positive to negative saturation. That's the parallel susceptibility, and as you would expect, you take the derivative of the hysteresis loop, and when the polarity changes, then you have the switching, right? Then the largest slope change takes place, and that gives you a singular peak because you're taking the derivative. So this is a singular point detection method. And that's what gives the sensitivity again, because you can look at this peak and then basically read off the switching field for this particular system. Now, when you do the transverse susceptibility, you notice that when you calculated this analytically, you notice you can actually get peaks on both sides along with the switching peak. Two other peaks are seen, and these are at the location of the anisotropy fields. Remember the first equation that I showed you? It's a competition between Zeeman and the internal anisotropy field. So these peaks are actually where the field is reduced and one dominates over the other. Okay? So they're at the location of the anisotropy fields. So you can read it off if you can measure these peaks. And that's exactly what we set out to do, because that's our exact geometry. We wanted to measure the transverse component of the magnetization, or this term right here. Oh yeah, we've been seeing these peaks ever since Srikanth was with me. Many years. We look at many different materials, ferromagnetic materials, nanoparticles, thin films, bulk materials, single crystals. We looked at a number of magnetic materials. This is an example for a manganite film. In a thin film, of course, the EC and hard axes are well defined, right? The directions are well defined, so you see really sharp peaks here, and that happened to be at the anisotropy fields. You can actually calculate the anisotropy constants and get the anisotropy energy, and these are one of the most fundamental energy scales in magnetism, right? It's as powerful as that. Now, for nanoparticles, you can see that this is basically, this gives you, you can track this as a function of temperature, so you can get some kind of a phase diagram, if you may, in the HT plane. You can track the way these anisotropy fields and switching fields evolve as a function of DC field and temperature. So just to give you an idea how we measure anisotropy. Okay, so now I told you that anisotropy is important. We have to use it, we have to tune it, we can measure it probably in the most sensitive way possible. So now we are in business. Let's see what we can use these nanoparticles for, especially for biomedical applications. Okay. All right. So if you think of magnetic nanoparticles for biomedical applications, here are some cartoons that tell you the story in general. You can use it for many applications. Let's start with this one here. One of the areas where magnetic nanoparticles are used is what is called targeted drug delivery or site-specific drug delivery. This is as opposed to systemic drug delivery. When you take a pill or you have an injection shot, right, the medicine is coursing through your entire circulatory system, and which means your whole body is feeling the effect, and there are side effects, right? Now, what if we just inject or present this drug exactly at the area where it's needed? And that makes it contained, and it doesn't affect the rest of the body. So magnetic nanoparticles can be used as navigational aids. For example, these nanoparticles can be functionalized with using ligand chemistry, and then you can attach various drug molecules, and then non-invasively using a DC field, you can inject these particles, and then using a non-invasive DC field, you can navigate to the area and release the drug. Okay, so that's an area where there's a lot of interest and there's a lot of work going on. There are challenges too, but these are areas that magnetic nanoparticles are being used for. Another area that we work in also, but I'm not going to talk about this, is that magnetic nanoparticles can be used for enhancing the quality of MRI images. MRI images, as you know, MRI scans are available in all hospitals everywhere, and basically it works based on the nuclear magnetic resonance NMR principle. What happens is that you're looking at the resonance or the precession of proton nuclei here, and what you do is that hit it with the field and remove the field, and then these protons, they relax. It's called the defacing, right? So there are two time scales here, two relaxation times, T1 and T2, and based on the T2, for example, T2 relaxation time is how these images are obtained. Okay. Now, it turns out that if you add nanoparticles to the area that you're looking at, the fringing fields, magnetic fields from these particles, they actually interfere with the T2 relaxation time. They change the relaxation time, they slow it down. And from that, you can build an enhanced contrast. So that's an area which is well established now, and in fact is used a lot in MRI contrast enhancement. I'm not going to talk about this, But the main area that I'm going to focus on now is actually using these magnetic nanoparticles themselves for treating cancer. All right. In this case, it's not being just a navigational aid, carrying drugs or anything. It's actually using the particles themselves for cancer therapy. So we're talking about theranostics, therapy and diagnostics at the same time with the magnetic nanoparticles. Okay. And how do we do that? We do that by magnetic heating or hyperthermia. So it turns out that these magnetic nanoparticles can be agitated by, under certain conditions, by applying an external AC field, and in the process they dissipate, and the dissipation is in the form of heat. Okay, and this can be used for killing cancer cells. That's the idea behind magnetic hyperthermia and how one can use particles, nanoparticles, for killing cancer cells. Okay, so here's how this works. The principle is that you can use magnetic nanoparticles, then using an external field, you can take it to the tumor area or inject directly into the tumor area, and then apply an AC field. That's the key here. And the AC field with a large amplitude, magnitude AC field at a certain frequency. And I'll discuss all these parameters so that you understand exactly what are the requirements here. You need a large AC field, high amplitude AC field, and typically the frequency is about a few hundred kilohertz. Okay? There are reasons for this. I'll discuss that. So that's what it's done. When you apply this, it generates heat. It generates heat through the form of hysteresis loops. Okay? And I'll show you in a minute how it does. But if you look at the biology aspect, what happens is that when cancer cells do not withstand heat, they don't like heat, all you need to do is increase the temperature a few degrees Celsius above the body temperature. So the window, the therapeutic window here is 40 to 45 degrees Celsius. That's what you need to do. You need to raise the temperature of the cancer cells, that area, the tissue where the cancer cells are, you have cancerous cells, to 40 to 45 degrees Celsius and hold it for about 30 minutes or so. And the cancer cells die. Okay? That's the idea behind this treatment. So the question is, how do we get to this and how do we hold this constant? So those are the parameters we need to work with. So in terms of how they die, you have protein denaturation and the cell membrane restructures, and eventually the cell deactivates or is driven to death. This process in biology, in biomedical area, nanomedicine, it's called apoptosis. Apoptosis is a benign way of killing cancer cells, okay? If you can think of it that way.
Normal cells, what is the tolerance?
Normal cells can tolerate a little higher temperature in general. But again, using the site-specific thing, we just target the cancer cells. And also, we can attach certain specific biomarkers that attach only to the cancer cells. All right? Okay. Ideally, you don't want to heat the normal cells, but there is some collateral damage, but we can live with that. Okay, so apoptosis is a very benign way of driving them. We think hypothermia is one such way of killing cancer cells. The other example is what is called necrosis. Necrosis is a brute force way of killing cancer cells. Can someone guess what necrosis treatment might be? Chemotherapy, radiation therapy. That's what is common these days in hospitals. And chemotherapy, of course, attacks everything, living cells, everything. And you see the side effects visibly, how cancer patients, how the immune system breaks down. Okay? There's a brute force method, works very well, but unfortunately has a lot of collateral damage. So the idea is to use magnetic hyperthermia as a supplemental therapy along with chemo. Chemo is still a really powerful technique. It's not going to replace chemo, but as a supplemental technique, hypothermia, magnetic hyperthermia can be used, and it can be effectively used between chemo doses and reduce the number of chemo treatments. Okay, that's the goal of how this treatment could be mainstream in hospitals. There's a lot of problems, of course. I can tell you three letters that keep us away from getting towards the application right now, and that is FDA, the Food and Drug Administration in the United States. There are similar agencies all over. They are rightfully so. They're extremely careful and extremely stringent rules to satisfy before they will allow transition to clinical treatment. Okay, so which is where we are. We are close to breaking this and convincing them that we can advance this to the clinical treatment. And I'm hopeful that in the next 10 to 15 years, this will be a mainstream supplemental therapy in hospitals. All right, let's now look at the physics of how this works. Okay. By the way, the good news is that there's only one company that I'm aware of that is actually doing this commercially, and this is MagForce, which is based in Germany, in Berlin, and they call it the nanotherm therapy, and they've been having very high, good success rate in this. And this has been noticed by the United States, and right now they have a subsidiary company in the US that just came in last year, and I understand that they've been given what is called IDE. This is an initial preliminary testing that FDA has approved for them to show a few cases, and they actually got their first prostate cancer patient last September. So they're going to, so that's good news that actually they're slowly coming into the market. There could be other companies that come up, and hopefully the FDA approval will be given for the clinical treatment. From the material science and physics point of view, I think we're right there. We can do all kinds of things. We can actually really have effective treatment possible with this technique. All right, let's look at how this works. We're talking about hysteresis loops here. But folks, these are not your DC hysteresis loop that you measure in your magnetometer. These are AC hysteresis loops. The difference is that DC hysteresis loops for nanoparticles, especially for 20 nanometer particles that we work with, will be zero. There will be no coercivity. There will be no hysteresis because these are super paramagnetic. And when they're super paramagnetic, you can think of each particle, nanoparticle itself being a ferromagnet, super spin, right? It's a collection of all these. It's a ferromagnet by itself. It has a large magnetization. But then there's no correlation between the particles, neighboring particles, so they're all randomly fluctuating at high temperatures. So when the thermal energy kBT is higher than the internal anisotropy energy of each of these particles, they look like a paramagnet because they're constantly fluctuating. You see a 1/T dependence, right? QT tail. And that's your super paramagnetic behavior. As you reduce the temperature, below a certain temperature, the internal energy, namely the anisotropy energy, exceeds kBT, the thermal energy. So these fluctuating moments, they freeze randomly. As a consequence, you get something that looks like a spin glass. And in magnetization measurements, you can see that as a drop in the susceptibility. So that's the signature of that. Again, spin glass is an important area that largely due to Professor Kerr in Hyderabad, he made it very famous, that particular field. So these are signatures that you can see similarly in nanoparticles. All right? So I'm getting to that. Yeah, it will be, typically we have to work with up to 1 kilo Oersted, no more than that. Few hundred Oersted to 1 kilo Oersted. I'm going to give you all the parameters. We need to work within certain limitations, and I'll explain to you why. Okay? All right, so what we need to do is apply an AC field at high frequency, and in this case the hysteresis opens up, and this hysteresis is because of the fact that these nanoparticles are trying to follow the high frequency. They cannot, they go out of phase, and that opens up a hysteresis loop. So remember that hysteresis means dissipation, right? Area under the hysteresis loop is energy that is dissipated. In this case, it is dissipated in the form of heat. So we want to maximize this area, and the figure of merit for this is what we call specific absorption rate, or SAR. It's also called specific loss power, SLP. It's one and the same. And what you want to do is you want to maximize the area and multiply it by the frequency, external frequency that you apply. That's your figure of merit. You need to have a large SAR for the particles to be effective and the heating efficiency to be good. All right? So that's one of the conditions. Easier said than done because we're dealing with nanoparticles where the magnetization is much smaller. But I can tell you, I'll show you later on, that you can actually make these particles very highly single crystalline and actually reach almost bulk magnetization. Okay? I'll show you some examples from our lab. Okay, so here's the physics behind it. I'm going to go through this very quickly. You can do linear response theory, and in fact, linear response theory works very well for anisotropic nanoparticles actually. So it's important to note that it actually applies very well to anisotropic particles. And then that's your loss power, and you see that it's a product of the field and the frequency. That's the most important parameter here. Now, what is the scale, the time scale here? That's governed by two time scales here. One is the Brownian. For example, the particle itself, because of torque, can move around mechanically. It can rotate, for example. That's your Brownian motion. The other one is the magnetization of the particles can move around. Okay, can try to follow this frequency. That's the nail relaxation. So it's a combination of this. And depending on the environment, one or the other will dominate. For example, if your medium is fluid, for example, then Brownian motion is possible. So Brownian will contribute. But in a cell, typically, it has a large viscosity. And so clearly mechanical motion is not possible unless it's at high fields. Okay? So depending on these parameters, you can actually see which one is governed, which one is dominating. In most cases, it's the nail relaxation times for these applications that dominates. Okay? Later on, I'll show you how Brownian relaxation is also used for this therapy. Okay, so to increase this specific loss power, or the SAR, one thing is you can increase the magnetization. Okay, the other one is there's some size dependence. I'll get to that in a minute. You can't have a size too small, and you can't have it too big. There's a sweet spot. which actually happens to be close to the single domain to multi-domain transition, okay, where the coercivity is pretty high, or the large value of the coercivity. That's where these particles are effective for this AC hyperthermia therapy. And there is very little is known about the influence of anisotropy. What happens if you change the particle shape? And again, as I showed you earlier, when you change the particle shape, you're giving it a preferred direction, for example, and that means you're skewing the hysteresis loop, which is precisely what we want, right? We want to play with the shape of the hysteresis loops. So it turns out that anisotropy actually could be important by looking at anisotropic nanoparticles to change the hysteresis loop itself and also the area, increasing the SAR. That's the case I'm going to make for you today. All right, so how do we measure the magnetic hyperthermia, or the SAR as I keep calling it? We do it in two different ways. One, in my lab, we use the calorimetric method. So there's this power supply here. This is an Ambrel system here, which supplies an AC field of about, we can vary the AC amplitude anywhere between 200 Oersted to about 1 kilo Oersted. Okay, that probably answers your question. And this works at a fixed frequency. In our case, it's about 325 kilohertz. There's a reason why these numbers are important. I'll get to that in a minute. So what we do here is that these particles are now in solution. They can be in water. They can be in a biocompatible solution. And they're actually in there in the coil. And we just measure the temperature directly of the environment by putting in a temperature sensor. Okay? So we record the temperature as a function of time. Remember, it's a rate we're interested in, SAR. Okay? And our data looks like this. The temperature rise as a function of time. Remember, the hyperthermia therapy window is 40 to 45 degrees Celsius. So we want to have a large slope to get to that window as fast as possible and then hold it steady. There is no need for you to overheat. There's no, of course, if your AC amplitude, the field amplitude is small, you'll never get to that temperature. Okay? And so in this case, for these manganese ferrite nanoparticles, the parameters indicate that you apply a 500 Oersted amplitude at 325 kilohertz, and you can actually get to this and actually saturate right there. So again, those are the handles that you have in terms of tuning your external parameters for achieving this goal of getting to this therapeutic window, holding it steady for 30 to 40 minutes. Okay, that's what you want to do. And this can differ for different particles and different kinds of particles. So you need to work with these parameters to be able to get to this. We can also measure the SAR by directly measuring the AC hysteresis loop. Okay, this is done by our collaborators in Spain for this project. We work with a group of Spanish researchers. What they did was they actually built an AC power supply themselves using a big capacitor bank, because you need to have a lot of power here. Okay, so they have this AC power supply, and in this case they actually measure the minor loops. They measure the AC hysteresis loops. You don't need to saturate. As long as you have a hysteresis, you can work with it. All right, you don't need to saturate it completely. So in this case, we can also extract the SAR with this simple formula, right? AC area multiplied by frequency. So we make these nanoparticle samples in our lab, do our measurements, ship it to Spain, and they do on the same system, they do the experiments. So we make sure that the SAR values match. So for the students in the audience, you know that if you want to publish in Nature Physics or Nature Materials or PRL, for example, you need to have a result reproduced by 2 different experiments. That's kind of the norm now. 2 different experiments are to converge to the same conclusion for a physical result. In this case, that's what we're trying to do here. Not just 2 different experiments, 2 different labs, even better. Okay, so this is something to keep in mind, and that's why you need to have collaborations ongoing collaborations. Okay, it's important to have this kind of collaboration. All right, so that's what we do. Now, I keep saying a few hundred kilohertz and also a few hundred Oersted is the limitation. Why is that? Why can't we just arbitrarily apply 10 megahertz or thousands of 1 Tesla? Why can't we do that? We cannot do that because there's what is known as the Atkinson-Brezowicz limit, which is a product of this in these units. That's the value there. Forget about the quantity. This is determined by the average pain threshold for a cancer patient. Remember, we're going to work with humans here. So we need to work with the pain threshold of a person, because this treatment is going to be prolonged for about 30 to 40 minutes. So these parameters are determined based on that for an average patient. It's not set in stone. You can go higher or lower, but this gives you an idea of typical range with which you need to work with. The pain threshold is something like, in the US, when you go to an emergency room, right? The patient, the first person that meets the patient is what we call a triage nurse, and it's probably the same in India. And so the triage nurse, the first question he or she will ask the patient is, on a scale of 1 to 10, what is your pain level? And of course, you say 2 or 3, or if you're close to dying, you say 9. So that's what this is, okay? So this is set around the value that can be tolerated by the average patient for an extended period of time. So that's why we need to work within these parameters. Okay, so all this is great. There's only one problem. It's a major problem. We can work with particles, we can try to increase the saturation magnetization. For example, iron oxide is right there. The SAR is very low compared to iron cobalt, or other magnetic materials. So why can't we use iron or iron cobalt alloy or anything like that? Permalloy or anything like that? We cannot use it because iron oxide is the only magnetic oxide that has been FDA approved. Nothing else. So you can see papers being published in all kinds of exotic, magnetic materials where they measure the SAR. It's meaningless because it's DOA, dead on arrival. You cannot convince the FDA to move on to exotic materials. We have to work with iron oxide. So this is something we decided early on in our group, that we need to do something with the existing material, biocompatible material, and try to improve the figure of merit. All right. So I'm not going to talk about exotic magnetic materials. It's only magnetic oxide, the basic fundamental magnetite is what I'm going to talk about. All right. So what else can we do? I already mentioned the size dependence. Anisotropy is a big question mark. So that's where we thought we will get into the action here a few years back. Since we felt that we can understand anisotropy, we can measure it very precisely, we can tune this. Can we play around with the shapes and sizes and see what effect it has directly on the SAR? Okay. So the first thing that came to mind, of course, and to others too, is that can we somehow fool these cells by having a biocompatible iron oxide shell and put iron inside, a core shell structure? Okay. So that's the first thing that came to mind, because if you look at the iron has a saturation magnetization of, bulk iron has a saturation magnetization of 220 EMU per gram, iron oxide is 92. So clearly, if you have iron core, iron oxide shell, which is completely biocompatible, then you have a biocompatible hybrid system with a larger magnetization. So you expect the SAR to be high. We thought so, and yes, it did, but there was a problem. I'll tell you that story. By the way, here are these core shell nanoparticles made by one of our wizards in the lab. We have several over the years. I'm not a chemist, so I don't go into this lab at all. It's all done by postdocs, generations of postdocs and students that have passed on their tricks that they learned, and we can make really high quality nanoparticles in the group. Okay, here's an example of a core shell monodisperse core shell system with iron core, iron oxide shell. Okay. So that's what we tried. We thought that we can increase the saturation magnetization and then increase the SAR. Okay, so those of you that do some chemistry, make nanoparticles using chemical techniques, this is how we do it. It's a very basic method. It's thermal decomposition is what we use mostly. But the way to do it is, it's easy to make nanoparticles. In fact, it could be a high school project most of the time in our group. They come and play, the kids play and make nanoparticles, take it to the TEM, look at it, and they're really happy. But it's really important to make single crystalline nanoparticles. This is quite challenging. That's what, you need wizards in the lab. Okay. In fact, we do have a competition in the group every year, like who produces the best particles, and we give them a title of Harry Potter, or if it's a lady, if it's Hermione. Okay. So, and it worked very well because they're constantly competing to make the best particles, and which is great for me. All right. So this is how we do it. I won't go into the details. Again, I'm not a chemist, so don't even bother to ask me exactly what is controlled. It's all done by simple control of the time, the temperature, and the surfactants that you use to control the particle size. Okay, we started with gold core and iron core and iron oxide shell. It turns out that there's something called Kerr-Kendal effect, which the chemists and the metallurgists knew years back, and that's a problem here. By the way, the word metallurgy is no longer existing these days. It's all merged into material science. Earlier it used to be Department of Metallurgy, right? And most of them have changed to material science. So what happens is that because of the difference in diffusion of the metal ion compared to the oxide ion, there are instabilities at the interface, and this causes voids to open up. So these voids increase, they get bigger and bigger, and finally the core disappears, it oxidizes. And then you are just left with a nice hollow shell. So the Kerr-Kendal effect ensures that if you make a metal oxide hybrid system core shell, you can get beautiful hollow nanoparticles. All right. It's great to make hollow nanoparticles. In fact, Paul Alivisatos in Berkeley was the one who showed this first, that you can make hollow nanoparticles by this technique using Kerr-Kendal effect. However, It's not going to work for hypothermia because your hypothermia, your SAR, is going to keep changing because the system changes. And in fact, hollow nanoparticles, the SAR drops. Okay? So we measured this. In fact, we actually measured the magnetization of the core shell particles, then the core getting smaller, hollow particles. We followed the whole thing structurally as well as magnetic properties, how they evolve. But that's not the intent of this talk. But basically what we showed is that you do get, look at this curve here, compared to the solid nanoparticles, which is black. I'm going to show the SAR in histograms now for comparison. Okay? It's easier that way. Pick any field you want. So solid nanoparticles, compared to that, the core shell with the iron core, iron oxide shell, which had a higher saturation magnetization, has a larger SAR. So indeed, the proof of concept worked. Okay? Indeed, we were able to get a larger SAR with the core shell particles. However, our happiness was short-lived because of this Kerr-Kendal effect. It starts degrading and eventually become hollow, and then hollow nanoparticles have no SAR. Okay? Well, the question is, this time that it takes is unreliable. We don't know. We can't predict how long this will take for different systems. So it's not something that can be reproducible. So we have to toss this and move on to other ways of making these kind of particles. So the next strategy we used, we wanted to follow the core shell. However, we need to make sure that the metal is not the core, because that's the problem, right? Metal diffusion and oxide diffusion is different. So instead, how about an all oxide core shell particle? And a group from Korea, actually around that time, scooped us. They actually made these cobalt ferrite, manganese ferrite core shell particles. This was back in 2011. And they showed that these are actually exchange coupled. Exchange coupling or exchange bias, as you may know, is something very important for the spin valve and MRAM community, right? That's basically, if you take a ferromagnet, antiferromagnet at the interface because of the spin pinning at the interface, due to the differential anisotropy, of course, what you have is your hysteresis loop can have a larger coercivity. You can also have it shift. This is well known in the spin valve and MRAM community. And it turns out that this exchange coupled, exchange biased nanoparticles also show a large SAR. So something that works for the spintronics community is also good for the nanomedicine community, right? Okay, some effect. So they showed that these exchange coupled magnetic particles had a very large SAR. But then, remember the three letters that I told you, right? FDA is not going to prove this. So we wanted to make something that is easier. It's an easier sell to the FDA. So we went back and wanted to make these same kind of a core shell oxide, all oxide exchange coupled system, but with magnetite. Okay, magnetite as the shell, the outer shell, which is biocompatible. So one of my postdocs, she was the Hermione that year. Okay, she made these FeO, Fe3O4 exchange coupled nanoparticles. Look at the exchange bias. We can actually, these are nano spin valves. Okay. These are nano spin valves. You can actually see the hysteresis loop shift, the coercivity increasing, and all that. Okay. So in this case, what she did was she had Fe3O4 outside and FeO. FeO is a lesser known phase of iron oxide. It's the Wüstite phase. It turns out that this is antiferromagnetic. So it's actually an antiferromagnet inside with a ferrimagnet outside. So it's an inverse core shell. Normally, if you make a core shell, the disordered shell and the ordered core is how it will be, but here is the inverse. Okay, so it's an inverse core shell, but it served the purpose because we now have an exchange coupled all oxide robust core shell system. There is no Kerr-Kendal effect here, no metal here, so this is going to be robust. Then on top of this, we wanted to play the game of changing the anisotropy. So using this core shell hybrid, it turns out that we can actually play what we call nanoparticle Legos. We can play with the shapes by changing the chemistry, the reaction time, as I said, so on and so forth. So we can make actually particles that are roughly spherical, cubic, and these are octopods. We compared these exchange coupled core shell particles by changing the shapes, okay, and the surface nature, and keeping the magnetic volume the same. Remember that we need to compare the values quantitatively, right? So in all these cases, the magnetic volume was kept the same roughly, and we can actually compare the results. And this is one of the most important slides of this presentation. For the first time, we showed how important anisotropy is, and it has a direct correlation of the SAR. For example, in all these particles, when you go to low symmetry, that is from spheres to cubes to octopods, the SAR is higher for the lowest symmetry. So anisotropy plays a key role in controlling or increasing the SAR in this case. So even with the same system, magnetite, biocompatible system that is approved by the FDA, we can still increase the SAR better than the state of the art. Okay? And we're trying to work with this company, Magforce, and trying to get them interested to use these particles instead of the conventional ones, commercial ones they use. I'm having trouble connecting with them, but we want to get to the point where we are able to use the anisotropy and tune the hysteresis loops based on these particles. Around the same, okay, then we thought this is great. So we were in a high here. So anisotropy really is important for increasing SAR, playing with the SAR, as I said. And so we wanted to see what else can we do. Well, we can make chains like the bacteria did, right? But then another group started looking at the SAR of magnetosomes. They actually started looking at the bacteria themselves, and they showed that these are showing very high SAR values. Okay? So we decided, can we make nanorods, solid nanorods, about the same length of these chains, and maybe change the aspect ratio. And that's what we did. We actually made iron oxide Fe3O4 magnetite nanorods. And for this, we use a different technique. This is a hydrothermal method. Those of you that work in nanoparticles know that if you want to get high aspect ratio particles, this is the best technique. This is like a pressure cooker. You're just cooking the particles, right, under high pressure. So we can get beautiful nanorods here, and we can change the aspect ratio to some extent. We can't, change it a lot, but we can change it to some extent. And it turns out that we did a comparison of the aspect ratio and found out that for these particles with this kind of an aspect ratio, they showed the best results. Okay? And here's a little thing. I mean, I still don't get it. I understand it. It's probably a coincidence. But we found that when the nanorod is about the same size as the chain that the bacteria makes, that's when we get the highest SAR. If you make it bigger or smaller, we don't get as good a SAR. So this is probably nature's secret, biomimetics. Nature's telling us something that this is the size you need to make. Okay? So this is something that I don't know, but it turns out to be a coincidental, interesting coincidence here, that the same aspect ratio works very well and gives you the highest SAR. So we measured SAR under various conditions here for these nanorods, and these are some of the highest values of SAR reported to date for these magnetite nanorods. You should never compensate on the quality of the particles. So for example, these magnetite nanorods, this is just the saturation magnetization is 86 EMU per gram. Remember that the bulk magnetite is 92. So we're almost there. So you can make nanoparticles with magnetization close to the bulk, but they have to be highly single crystalline all the way through. Okay? And we can show that using high resolution TEM. The other quality check in magnetite, turns out that those of you that know about magnetite, it has one of the most celebrated metal insulator transitions. It's called the Vervet transition. Happens at 125 Kelvin or so. Okay? Nanoparticles, you can almost never see that. Turns out that you can see it if you make high quality particles. So this is the Vervet transition, the signature of that in susceptibility. Very sharp transition for these nanorods. Again, if you make highly single crystalline particles, nanoparticles, you can see the Vervet transition, and you can ensure that as a quality check for the high crystallinity. How much time do I have? 10, 15 minutes or 10 minutes? All right, okay. So the story here is that particle size is important, but quality is important, single crystallinity is important, and also play with the particle surfaces and shapes and sizes. Now we are working with iron oxide and cobalt ferrite. Again, keep in mind that the cobalt ferrite is inside. We have the iron oxide outside. No Kerr-Kendal effect, all oxide. There's no degradation. Why cobalt ferrite? Because cobalt ferrite is the only ferrite that has the highest magnetic anisotropy. So we think that this could play a role in changing the hysteresis loop further and increasing the SAR. So this is what we're working with. We're getting some nice results, but we need to fine tune this process, so it's not quite ready for publication yet. But I just wanted to show you that indeed these are important systems that can be done. Then we also thought about ways of combining and making hybrid nanoparticles with gold magnetite or silver magnetite clusters. Remember I talked about configurational anisotropy, right? Making clusters. Turns out that gold is even better. We made it with silver and gold. And you can actually have a gold nanoparticle because it's polyhedral. Gold can nucleate the growth of iron oxide which attaches to it in the form of petals. You can make these small nano flowers. And the reason is, if you look at the lattice constant of gold and magnetite, they are just by a factor of 2. So you can have epitaxial surfaces. Remember, high quality is important. So if you have epitaxial surfaces, you have single crystalline, you can see the planes right up to the surface, right? So when you make these specific particles, we can get really high SAR. The other reason we made these gold in this form, because you can always have gold shell and ferrite core, right? That's a normal way of making a gold ferrite core shell structure. In this case, we wanted both the iron oxide as well as the gold surface to be exposed for functionalization, because gold can have thiol chemistry and you can attach ligands. So we want both these surfaces to be exposed for functionalization. So we made these structures. The other reason is that it's not just magnetic hyperthermia. You can also heat up locally by using metallic nanoparticles. For example, if you make gold nanoparticles, 10 nanometers or something like that, and if you hit it with a laser at the right frequency, right power, you can actually induce or couple to the surface plasmon resonance. This is well known in gold, right? So that can be used for heating too, metallic heating. So in this case, we can actually have two different dual functional heating. So we tried that under different combinations, with just the gold being subjected to the laser, and then just the AC, and then the combination of both at the same time. And of course, as you can expect, when both are present, the heating is much faster. The efficiency is much faster. All right. So this is combining magnetic and photothermal hypothermia. We also showed that that works. A question that I always get is that how are you going to take the laser into the human body, right? There are ways to do it. There are fiber optic lasers. You can do that. And also remember, this technique is mostly for superficial tumors. It's, if you have pancreatic cancer, I don't think you rely on magnetic hypothermia. You still have to rely mostly on chemotherapy. And also remember that this is a supplemental therapy. We want this to improve the patient's life quality by reducing the chemo dose. By having this treatment between chemo doses so that you can reduce the chemo dose, you can increase the time interval between the chemotherapy. Okay, that's the intent for this particular technique. All right, everything that I told you is only half the story. No, I'm not going to give another hour of extending it, but this is speaking from a physics and a material science point of view. I've told you that you can still keep the same basic system and still improve the SAR by playing with the surface and the shapes and things like that. But in every system that you make, you have to demonstrate cytotoxicity. Or in other words, you need to check the cytotoxicity. You need to do measurements and show that they are not toxic. Otherwise, again, it's not going anywhere. This is very important, and for this I'm going to show you some results. This has to be done. There's no other way. If you want to convince, right now if you want to publish papers in hypothermia, just reporting hypothermia is not enough. You need to show that they are biocompatible. You need to do cytotoxicity experiments, to publish in a good journal with a high impact factor. Okay, so this one shows that on nanorods, for example, cells love to eat these particles. I've seen them under a microscope. They actually go and eat them. You can't see them right away. You incubate it overnight, and the next morning, and this is what graduate students are for, the student will look into it and start counting how many cells died, how many are alive. This is the only way you can get cytotoxicity results from statistical cell death rate. Okay, and that's how these. This one is a nice movie. I wanted to show you this. This is actually sent to me by some friends in France. They created this fast. So those are actually cells that are grabbing the nanoparticles and eating them. You can see that they're almost like ants grabbing something. So you can see that this is a fast video over time, and you can see that's how they basically ingest these cells. They love eating the particles, the cells. The cells will take the particles inside, but then it's interesting because we tried with different particles. They like the nanorods, but they like the nanorods only if they are not in bunches. So they don't like nanorods sticking together. They avoid them. They didn't like the hybrid particles. They avoided them. They loved the core shell particles. So you have to work with what they like. You have to feed the cancer cells what they want and give them toxic doses so that they die peacefully. Apoptosis. That's the name of the game.
Normal cells don't like them.
No, yeah, normal cells also take them, but you have to make sure. That's why the biocompatibility is an issue. So you can actually do cell separation afterwards. All this is, as I said, is done in vitro. We wish we can do in vivo. We can't do it. We can only do rat models. We can inject it into a rat and then see the tumor reducing. That has been done by many groups. Right now in the US, we're still working with rat models. We're hoping that Germany is far ahead. The European Union has put a lot of millions of euros into that program, and they've actually produced results, this company. And now, hopefully it's coming into the US system, and we'll be able to translate it or transition it to human trials. Right? All this is in vitro.
Do you have additional surface this treatment to make it biocompatible?
Yes, yeah, we can do that. The most common ways are you can actually have various kinds of ligands that are targeted ligands that can specifically target certain cancer cells. You can also have fluorescent dyes, so you can follow them around, which cell is doing what. And also, there are many things. For example, people use PEG, polyethylene glycol. You know what else PEG makes up? Contact lenses. One of the most biocompatible you can think of. You stick it into your eye, right? So it's called pegylation. So PEG is very, very good. Dextran is used. Some form of glucose, sugars, they're all used to coat these particles. Okay, so there are various ways of making it biocompatible just beyond Fe3O4.
So these assays are done only in cancer cells, right?
Yeah.
Not to mixtures of healthy and cancerous cells to compare them.
No, they've done it in mixture too. And again, as I said, there are certain ligands that are attached to these particles that do not attach to the living cell, the healthy cell. It goes only to the cancer cell. There's some chemistry involved. I don't know much about it. There's a biochemical reaction that's involved. So that's how it is done.
So it will preferentially attach.
Preferentially attach. There'll be some living cells that'll die, but some healthy cells that'll die, but it'll preferentially attach to the cancer cell. That's the idea of this particular type of decoration that you have for these particles.
What is the shape of these particles that you apply IAC?
Can you what?
Stability of the shape of these particles.
The stability of the shape of the particle, that's a good question. These particles are fairly stable as far as the shape goes. However, there's another kind of treatment, I'll get to that, where actually you can use the torque that you generate by an external field to agitate these particles and physically tear apart the cell walls. This is what is called magnetomechanical therapy. Okay, there's another entire set of groups that work on this magnetomechanical. I'll mention some names as I conclude this presentation. All right? Yes.
Sorry, I'm not a physicist. I'm a life scientist. So, you said you can inject these particles by non-invasively. How do you do that?
Non-invasively, you can guide these particles because these are magnetic particles. They have large magnetization.
Okay.
And you can use an external magnet outside the human body to sort of hold them and then drag them around.
So even for the internal tumors?
Ideally, you want to inject close to the tumors, not to the internal tumors. That's very hard.
Okay.
Right now, I think the most effective treatment for tumors is the ones that you can see superficially. For men, it's prostate, and for women, it's breast. These are the two types of tumors that can be effectively treated with magnetic hyperthermia. Tumors that are deep inside, pancreatic, for example, is one of the most dangerous forms of cancer, where basically the time from the time it is detected, it's almost too late, right? So that it's difficult to see how one can target that.
So you don't have any data related to the...
There is some data, people have tried that. They've tried that with rat models. Okay, with rats. With humans, except for this company's data, we don't have anything yet. Okay. Alright, so let me just go ahead and conclude this thing. I showed you this thing. Oh, I'm going backwards. No, I have to go the other way around. Why is this stuck? Nothing happened here. Sorry. Oops. I see a message that program is not responding. But it's not the deadly blue screen, so there's still hope. Okay, so we've shown this that indeed having these cells with the particles in them and then applying AC fields does work, and the cell death rate is higher with these parameters combined. Okay, so that's effectively shown. I just talked about other ways of using magnetic particles for killing cancer cells. This is there are two different groups here that I've shown. There are many other groups. This was first proposed by the Argon group back in 2010. What they do is that they make some kind of synthetic antiferromagnets. Basically, they can control the shape and the anisotropy of these particles, the shape of these particles, so that the torque is maximized at low AC fields. When you have that, then the frequency at these low frequency and low fields, these nanorods will start spinning like a motor. You can actually have a motor, and that will rupture the cell walls. So that's another way of destroying cancer cells, magnetomechanical. And most recently, Russell Colburn has been working on these so-called micro discs with vortex states and using that to maximize the torque. and increase the magnetomechanical way of killing the cancer cells. There's of course a debate as to which one is apoptosis. I think both of them are apoptosis compared to chemotherapy, which I believe is necrosis. All right. This is like the Dr. Jekyll and Mr. Hyde, controversy. You need both. All right. This is what I said that last year is when this company has come into the U.S. and the FDA has given them this investigational device exemption, which is giving them the go-ahead to show some case studies based on which they might give approval, but this process could take 3 to 5 years. So that's the thing. It's a very painstaking process here with the FDA. For anything that we need to convince them, it takes several years. This is the reason, please stick with magnetite. Don't go to other materials because it's never going to be approved anytime soon. That's pretty much the end of my story. I would like to plug my journal here. I'm an associate editor for Journal of Applied Physics, and we do accept papers in a wide area of range of fields. Magnetism, of course, a lot of papers published in this journal are on magnetic materials, spintronics, and so on. We also are taking papers in biophysics. So somebody working in life sciences, consider if you have any applied physics angle to this, please send it to us. So that's the summary, but let me just say the summary in a different way. So size does matter, but no, we're not talking about the Godzilla kind of size. It's nano size, but hopefully today I've convinced you that it's not just the size, it's the shape, surface, and interface. There is an issue about size that I need to mention because it's very critical. You cannot have particles less than 10 nanometers and inject them into the human body, period. Because if you have very small particles, it can penetrate the blood-brain barrier, end up in the brain. Instead of going down south where it's supposed to go, goes to the brain, and that you don't want. You don't want particles going to the brain. You want the particles ideally to be screened by the natural mechanism, human mechanism, antibodies covering it or whatever, and as if it's an infection. Or you can have the liver or the kidney act as screens. It's kind of benign compared to going to the brain. Okay, that's one thing you want to avoid. So there's a size restriction for the particles. This is why the most effective treatment is going to be with particles that are 25, 30 nanometers or higher, more in size, not below that. Okay. As I mentioned, play around with the shapes and surface and interfaces. That's where the excitement is. That's where the prospect of increasing the SAR using the same biocompatible magnetic oxide. So with that, let me conclude with some pictures of my group. And my last slide here is I would like to, on behalf of my Functional Magnetic Lab group and also the IEEE Magnetic Society, thank you for your attention. And as you can see here, like most of you here, members of my group, some of the best research discussions are done in coffee shops and in bars. Thank you very much.
Good evening, everyone. I've been given the task of delivering the note of thanks, or however you want to term it. Right. Actually, we are honored to have Professor Srikanth among us today. We are all very thankful to him for giving this wonderful talk, and I hope the students also found the lecture very engaging and they are now inspired to take up research after their masters. I have known Professor Srikanth from my PhD days when I was a graduate student at USF, and as he told you earlier, he was a member of my doctoral committee. So it's always a pleasure to meet him now, right? So, yeah, so, and I'm under no stress that, God, what's going to happen next? So, and I sincerely, and we sincerely hope that this will not be his last visit at University of Hyderabad, and we will get many such opportunities to hear him again here. So, we are able to organize this lecture due to the combined efforts of School of Physics, Public Relations Office, and VC's office. So on behalf of the organizing committee, I would like to thank Dean School of Physics, Professor Bindu Bamba, for giving her consent for organizing this lecture. I thank our Honorable Vice Chancellor, Professor Appa Rao, and his office for making all the necessary arrangements. Also, I'd like to thank Public Relations Officer, Mr. Ashish Jacob Thomas, and his office, especially Mrs. Vijaya, for preparing the posters announcing this distinguished lecture. Thanks to our Pro-VC, Professor Arun Agarwal, for presiding over this lecture today. I thank Professor Rajaram for delivering the welcome note, and Professor Srikanth for the introduction remarks. I would also like to thank Dean School of Physics and her office, especially Mr. Shekhar and Mrs. Shailaja, for making the necessary arrangements. And also UGC Center for Advanced Studies, School of Physics, for supporting this lecture. I will also like to thank Estate Section for making necessary arrangements in this Raman Auditorium, and also like to request them to please fix the AC as soon as possible. Finally, I'd like to thank all the faculty members of School of Physics and University of Hyderabad for joining us today, and the students and other participants, and making it a great success. I hope that there will be a high turnout like this for any future lectures like this.